The purpose of a heat exchanger is to transfer thermal energy from one liquid to another. A heat exchanger aims to optimize this heat transfer while still maintaining a strict segregation of the liquids.
Before we go into the details of a plate-type heat exchanger, let's go through a real-life comparison of humans and heat exchangers.
Let's assume that James is happy, like in this picture, so we know he must be drinking beer in the pub.
Now, let's also assume that Sean is stressed out about his exams tomorrow.
Watch what happens when they pass in the pub. When James passes stressed out Sean, he gets a little stressed out as well.
And when stressed out Sean passes happy James, he gets a little bit happier. They exchanged emotions the same way fluids exchange heat inside a heat exchanger.
In this animation, we see how the two liquids flow within the heat exchanger. The cold liquid, shown in blue, flows upwards. The hot liquid, shown in red, flows downwards. This is called counterflow and serves to maximize the temperature differential between the two liquids at any point in the system. Again, we can see that the hot and cold fluids are always separated by one plate.
We have a plate-type heat exchanger located in the Haverly Laboratory, which is used to cool the cooling water on the dynamometer located on the Detroit diesel engine. Hot water from the dynamometer enters the plate-type heat exchanger here, passes over plates, which we'll talk about later, and exits here. Cold water from the cooling tower outside enters the heat exchanger down there and exits up here. Important features of the plate-type heat exchanger are the stack of plates located behind the shroud. We'll talk about those a little bit more, but the plates all look like this, and they're stacked together in this fashion. Through the heat exchanger, you can see these tightening holes, which are much longer than they need to be for the size of the heat exchanger. This is because you can take off these bolts, move the back of the plate back, and add or reduce plates as necessary. More plates obviously results in more heat exchange.
Here we have a plate from a plate-type heat exchanger. Some key features to note are the corrugations, which increase the rigidity and the surface area of the plate. By increasing the rigidity of the plate, we're able to use a thinner metal, which facilitates heat transfer. We have a gasket that runs the perimeter and segregates the two liquids. Here, one liquid passes and exits there. The liquid on the other side does the same, but in the opposite direction. The space that's in between these gaskets is called the telltale. This is so that when one side of the gasket leaks, it'll be seen by the operator before the liquids can become contaminated.
In addition to the advantage of being able to remove and add plates to achieve the correct level of heat exchange, the nature of the plate-type heat exchanger also allows for ease of cleaning in a very small space. You only need this much distance to remove your plates and clean them or replace them if necessary. And these little plates are pretty thin, there's not much mass to them, so they're pretty cheap. And you can store lots of spares on board without taking up too much space or adding too much weight. This is one of the distinct advantages of the plate-type heat exchanger over a shell and tube, where you need twice the length of the shell and tube heat exchanger to remove tubes to replace or clean them.
You can see in this animation that the hot fluid is cooled and the cold fluid is warmed within the plate-type heat exchanger. But we asked Professor Wiggins why the cold fluid didn't get colder and the hot fluid didn't get hotter. There's still the same energy transfer. He told us that entropy can't be decreased in the process, so that it will only work in one direction. When we asked him what entropy was, he responded to us,